This discussion is going to focus on the development of the model of the atom. In this slide, we see a picture of the model of the atom that you're probably the most familiar with, where you have protons and neutrons in the nucleus, which is at the center of the atom, and then electrons orbiting around the outside. We're going to talk in this discussion about how we developed this particular model, and then later on in this unit we will look at the deficiencies of this model and how it was improved upon to get the current model of the atom. Okay, initially when they were thinking about the concept of an atom, it was imagined to be kind of like just a ball, a solid ball, solid particle. And one of the things we're going to talk about now is how did we get from that model up to the Bohr model, the model that, again, that you're probably the most familiar with. And the thing that I want you to really recognize is that there really wasn't one single person that came up with all parts of this model, that really it was scientists building upon the work of other scientists and refining and improving, which is really the process that occurs in all areas of science. So we're going to kind of focus in on that in this discussion. Okay, so beginning with Democritus, he was a Greek philosopher, not one of the more well-known ones, which is why it took so long for his model of the atom, or his concept of the atom, to be accepted. But he basically thought about what matter was and decided that you could keep having matter, keep dividing it into and dividing it into and dividing it into, and then eventually you would get down to a particle that you could not divide again. And so he's the one that we credit with using the term atom, or atomos, which means not to be cut. Okay, and so this is kind of showing what his concept of matter was. Okay, and again, he was not the most popular Greek philosopher, and so it took a long time for people to really accept his model and develop it. And the reason is, Greek philosophers that you probably are very familiar with, Aristotle and Plato, had this other theory that all matter was composed of 4 components: air, fire, water, and earth. And they combined in different ways to create all of the different types of matter. So here's kind of a timeline, and we can see that here we had Democritus, let's see, kind of way back here, and then up until Dalton in 1803, they had the whole air, fire, water, and earth model. And Dalton, which we'll talk about in just a second, was the one that basically brought in Democritus's model. Okay. Dalton was an English chemist, and he performed lots of experiments on his own, but again, he also pulled in some of the laws that were developed by other scientists, and he developed Dalton's theory. This is a very basic theory of the atom, and here it lists it in 4 parts. I think it's similarly listed in your book. Please note that I want you to be familiar with what is in Dalton's theory, to the extent where if I gave you a list of statements, you would be able to pick out which ones were part of his theory and which ones were not. I don't need you to be able to completely regurgitate this on a test, but I do want you to understand kind of the basics of what was in his theory. Okay, and so he brought in Democritus. All elements are composed of atoms. They're indivisible, indestructible particles. Atoms of the same element are exactly alike. Atoms of different elements are different. And we get compounds by joining atoms of two or more elements. Some of these were changed slightly, basically with our knowledge of nuclear reactions. It changed some of these. Our knowledge of subatomic particles changed some of these. But the basic foundation that he laid still applies. Okay, so now here we come up to expanding on the concept of the atom as to what exactly is it. And so we have a scientist, J.J. Thomson, and he did a lot of experiments with cathode ray tubes. And here's a picture of a cathode ray tube. And basically, this is a glass tube that you've pulled all of the air out of, draw a vacuum on it, and it has electrodes at either end. So, like here you see they've got an alligator clip clipped to here and here. Okay, so we're going to basically use this setup here to pass electric current through here. And as you can see, what they observed with these cathode ray tubes was that when they did this, they got this beam. And so if you see right here, this little glowing thing, it's glowing kind of green. And the thing to realize there too is that this, and you can look at the one I have in class, which is exactly like this one. There is a little slit that, and I'm not sure which end is which on this particular setup, but there is kind of, you can see there is a plate, a metal plate that's right here, and there's a little bitty slit right there, and so that's what makes this look like this narrow beam. Okay, if this slit weren't here, you would kind of see, well, the cathode rays would kind of be all around on this in the cathode ray tube. But the little slit here forces a beam, or the particles, to go through this little slit. We have a beam that's created there, and essentially this glow that you're seeing here is the interaction of that beam with this piece of metal. Has like a phosphorescent coating on it, and so when the beam touches this coating, the molecules are going to glow, and so that it just helps to make the beam more visible. So, and you'll be able to see it more on the one I have in class. And basically what he did, there were lots of experiments that were done with these cathode ray tubes. They created one that had a little paddle wheel in it, and when they set it up and passed the current through it, the paddle wheel would rotate. And that basically told them that, oh, this beam has particles in it that have mass, because they're able to impact this paddle wheel and cause it to turn. The other thing, and this is the thing that Thomson is given credit for, is that they noticed that when he put a magnetic field, like if you put a magnet next to the cathode ray tube, like here's my little magnet, okay, what they noticed is that it would cause a change, or cause a change in the path of the beam, and that the negative end of the magnet, or a negative electric field or magnetic field, would basically repel the beam, would push it away.